I hope I am clearly visible. My slides are also visible and I am audible to everyone. So, welcome to today's session on water and wastewater treatment. This is third week, and I am Saptarshi Bose, PMRF Research Scholar from IIT Madras. As usual, we will try to solve few questions which are similar to the assignment questions. Also, this will be helpful for you to solve the questions in your examination, upcoming examination conducted by NPTEL. And not only this program, this live session will clear your doubts, conceptual doubts, as well as numerical doubts. And at the end, when you will go for any other examination, say GATE examination or any job examination, it will definitely help you. So we'll move forward for today's first question. Now, this is a numerical type question. I will request everyone to solve. At least you should try to solve. You can refer your book, you can refer your notes for the formula if you don't remember right now. And use your chat section or the in-call message section to write your answer. You can just type your answer there. So I can get your answer. There is a spherical grit particles having a radius of 0.01 millimeter and specific gravity of 3. It needs to be separated in the settling chamber. It is given that G equals to 9.81 meter per second square. The density of the liquid in the settling chamber is around 1000 kg per meter cube. So it is water, you can say, and the kinematic viscosity of the liquid in the settling chamber is 10 to the power minus 6 meters per second. You have to assume the laminar flow condition and now calculate the settling velocity. You can refer your notes, you can refer your books for the formula if you cannot remember. Okay, very good, Nicholas. I got the first answer from Nicholas. Okay, I'll wait for others to answer. Please quickly calculate and give the answer. Then we will check what is the correct answer and we will try to solve this. 2 more minutes, then I'll go for the solution. Let's try to calculate quickly. Okay, so I think we should not wait for more time. So we'll go for the solution. If someone is trying, just let me know. Then I'll wait for 1 more minute. Others will go for the solution. So the correct answer is pardon. So the correct answer will be here 0.35 to 0.45 millimeter per second. So we'll check how to solve this. So Nilkesh, check your answer. So we know how to calculate dynamic viscosity from kinetic viscosity, right? So this dynamic viscosity mu will be K multiplied by the rho. So what is the value of rho here? The it is given as the density as given as 1000 kg per meter cube, right? So this is my rho value for the liquid, and K value is also given. Uh, K value is given as this is a kinematic viscosity given as 10 to the power minus 6 meters square per second. So 10 to the power minus 6 meters per second multiplied by my density of the liquid, that is nothing but 1000 kg per meter cube. If you do the calculation, you will get 10 to the power minus 3 kg per meter second. Now we know the settling velocity formula for laminar flow. That is nothing but G multiplied by in the bracket rho P and this rho W multiplied by dP square divided by 18 mu, right? This is my settling velocity formula for any particle in a liquid which is traveling in the pattern of laminar. So now you just have to put the values, nothing else. So the G is given as 9.81 meter per second square. That's our usual value, 9.8. You can take. Then one interesting thing is given as the specific gravity of the particle is a spherical particle, and the specific gravity is V, right? So you know how to calculate density from specific gravity, right? So specific gravity, pardon for the pain issue, specific gravity is equals to your density, or you can write as this. So your density of the particle divided by density of the water. So if I want to calculate what is the density of my particle, rho p, it will be specific gravity multiplied by rho W, right? So I'll get what? Rho P. So this is my density. Rho P is my density. I'm multiplying specific gravity of that particle with the density of water. So that's what I have done here. 3. It was the specific gravity multiplied by 1000. And here only 1000 because this is rho W. So rho W is 1000 kg per meter cube. And then this is 2 multiplied by, because that was the radius, you need to put the diameter. So 2 multiplied by 0.01 into 10 to the power minus 3 to convert it from millimeter to meter, and it is square. This is already calculated, 10 to the power minus 3 kg per meter per second. This is the mu value. Put the mu value, calculate, you will get this. So it is as simple as that, right? So let's go to the next question. I hope this is clear. It's a theoretical question. Consider the following treatment steps in a conventional wastewater treatment plant. So you have to say what is the correct sequence of these steps or the units. This is a very easy theoretical question. I expect everyone should answer this. So use your chat section or in-call message to write your answer.
Answer is C.
Okay. Thank you, Abdul. Yeah, I got answer from Ruchita C and Dilkesh also. Okay, so the correct answer is C, and I hope all of you, I think, who are present, maybe except one or two, said it correctly. So the right sequence is the screening, then it will go for the grit removal, then the primary sedimentation, then secondary treatment unit, then we have to remove the sediment, biological sediment, at the end we can go for the desalination. So the next question, again theoretical question. In aerobic conditions, the microbial decomposition of organics result in the formation of which of the following? Okay. Yes, I got answer from Kanchana A, and then Nikhilesh A. Anyone else want to answer? So, okay, Ruchita A. Fine. So the correct answer is A, right? So the in case of aerobic conditions, the microbial activity actually stabilize the end product, and also it will not create any unobjectional end product. But in case of anaerobic condition, what will happen that there will be methane and carbon dioxide, right? So sorry, in case of uh, this is the aerobic condition, right? And in case of anaerobic condition, there might be H2S and other gas which are objectionable. So this pardon, this is the in case of aerobic, it will be methane and carbon dioxide only. So you won't get much smell. But if it is generating H2S, then it is a smelly end product. So the next one, again numerical question. A water supply board is responsible for treating 1500 meter cube per day of water. Settling column analysis indicates that an overflow rate of 20 meter per day will produce satisfactory removal for a depth of 3.1 meter. It is decided to have two circular settling tanks in parallel. So the required diameter expressed in meter of the settling tank is that you have to calculate. Ah, very good, Ruchita. You are saying that 6.9 meter dia of each. Okay. So what about others? Others, please try to answer. Try to calculate quickly. Okay, Nikhilesh, 6.9 meter. Very good. All of you were very quick. So I'll wait for maybe 1 more minute. Very easy one. No need to wait much. Okay, fine. So the answer is 6.9 meter. Congratulations, Ruchita and Nikhilesh. And so two tanks are in parallel. So flow of each tank will be how much for the total? Okay, 1500 meter cube per day. So it will be 750 meter cube per day. And then the overflow rate is 20 meter per day. So you have to, sorry, this will be 20, right? 750 by 20. I'm getting the surface area as 37.5 meters square. This was the overflow rate. So this surface is our main thing, right? So it was for the surface, and then the area A equals to pi by 4d square. That is nothing but 37.5 meters square. So from here you can calculate the diameter as 6.9 meter. So I hope this is clear for everyone. Next, again, theoretical question. The microbial quality of wastewater effluent is usually monitored by which process or instrument? Okay, good. Wichita B, fine. Okay, Nikhil's is saying that MPN test, fine. That is again B option. What about others? Please, if you can try to answer. Okay, fine. We'll go for the answer. No more response. So the correct answer is the coliform MPN test. This is the easiest process to identify the microbial colony, and from there we can calculate and get the assumption of microbial activity. The next one, again, theoretical question regarding the pre-treatment process.
So answer is A, bar screen and grid chamber, that is coming first. Then after it is going to flow equalization.
Okay. Yeah, thank you, Abdul, for your answer. Very good. So I'll check for others. Yes, Ruchita, A and B. Fine. Nikhil's A. Okay. So the solution is A and B, right? Abdul and Ruchita, you are correct. And Nikhil is So the first one is this bar skin and then grit chamber. For the very broad like coarse particles, we are using this bar skin. Then to remove the grit chamber, and after that we need to equalize and also proportionate intent, because otherwise, in the different hours of a particular day, the flow rate varies, is not same always. So that is also very necessary to equalize. Sometimes around 8 a.m., suppose this is at a peak, and then again around 7 to 8 in the evening it is peak, and then it's going down, something like that. So that is the trend. So suppose from this 8 to 10 there is a peak, and then again from 7 to say 9 there is a peak. So this line will be a little bit higher. Sorry, not here. So something like that. So we need to equalize whatever the flow is coming to the system, the treatment plant. Otherwise, what will happen that the biological system or the secondary system will face a shock of the organic matter loading, of the water loading. So it will not function properly. So it will be difficult for remove the nutrients as well as organic matters and other stuff. So next question number 7, numerical one, easy one, same as the previous thing. With grid chamber, with dimension, flow rate. You have to calculate the surface overflow rate and the hydraulic retention time. Okay, I got answer from Ruchita, this D, and Nikhil is D. Right. So we'll go for the correct one answer. Yes, the correct answer is D. That is 40,000 liter per hour per meter square, and 1.2 minutes the detention time. So first we need to calculate this surface overflow rate. So it is nothing but 720. 720 was the flow rate, 720 meter cube per hour, and divided by your dimension L and B, right? That's how we calculate the surface overflow rate. So this 12 meter and 1.5 meter. So if this is the thing, this is the way, in this way the water is entering, and this is my surface. So this is the length, and this is my breadth. In case of surface overflow rate, the depth is not required, it's not related anyway. So this area is only required. This is 12 and this is 1.5, 1.5 and this is 12. So 12 multiplied by 1.5 area, and this is meter cube. It was in the unit of meter cube, not liter, meter cube per hour. So I'm getting surface overflow rate as 40 meter cube per hour per meter square, and then you need to convert this meter cube to liter. So if you convert, it will be multiplied by 1000, and I'm getting 40,000 liter per hour per meter square. Next is the detention time. That is nothing but the volume divided by your flow rate. And here the flow rate was how much? 720, right? So pardon for this will be 720. And this is 12 multiplied by 1.5, and this is 0.8. And we are also converting this hour. It was, see, this was in hour. So I'm converting this into minutes. So multiplied by 60. So if you just calculate, you will get 1.2 minutes. Hope this is clear for everyone. I'll move to the next question. Again, theoretical question related to the ideal sedimentation tanks. Multiple options may be correct. So answer wisely. Okay, I got first answer from Nikhilesh. That is B, C, and E. Anyone else? So the correct answer will be A, C, and D. That is the type 1 settling is assumed in case of RDL sedimentation tank. Then the particles entering the outlet zone are removed with the water, and then last, the even distribution of flow entering and leaving the settling zone. So that is for the ideal condition. So this is the ideal condition we are assuming. Thus the assumption and this non-uniform distribution of particles, no. And also the particles entering the sludge zone are not captured. So the next question, again a numerical type question. It's a pool of data. So read by yourself, and at the end you have to calculate what is the organic fraction of the solids in terms of mg per liter. This is a very easy question. No need a big formula. Just use your concept and you can solve this. All the data are given in the question. Please try to solve this within 1 minute, then we'll go for the solution. Because we shouldn't wait for a longer time for this question, particularly. Okay, Ruchita, fine, 2 minutes. You can take, no problem. Okay, Ruchita, I got your answer. Is it D? Fine, I will check. So the right answer is B, I guess, 25,000. Please check calculation. It might be wrong from my side. I'm just telling you the process, but you should calculate by yourself. So be careful about that. One information is given as the crucible weight. The only crucible weight, dried crucible weight, is 62.485 gram. So this information is not actually needed for this particular question. So we don't need to use this. It's very simple. What was the process? First, the only crucible was weighed, and it was found that the weight is 62.485 gram. Then 75 ml of well-mixed sample was taken in that crucible. After that, we went for the drying of that crucible in a drying oven. Temperature was 104 degrees Celsius, and after that we got a mass of 65.02 gram. So from here we can start. Then this crucible was dried, crucible, sorry, with the dried sample was placed in a muffle furnace, and it was placed at 600 degrees Celsius for an hour. Now, what is the remaining there is not the organic fraction. So from these two statements, you can easily understand that whatever is gone, that is my organic fraction of the solids present there. So after cooling, we got the mass as 63.145 gram, right? So these organic fraction of the solids are gone. Residual are not that organic fraction. That's why it's remaining in that crucible. So how will we write? The weight of the sample at 104 degrees Celsius is 65.02 gram, and the weight of sample at 600 degree after, like, we should say after 600 degrees Celsius temperature, it is I'm getting as 63.145 gram. So whatever the organic matter was there, it was converted into carbon dioxide, water vapor, and other gases at 600 degrees Celsius. So you can say that 65.02 minus 63.145 was the organic portion, and the sample volume was 75 ml. I'm dividing this, and this was in gram, multiplied by 1000 to make mg, and then again multiplied by 1000 to convert this ml to liter, right? So at the end, I'm getting 25,000 mg per liter. Yes, and Nilkesh, you were right, 25,000 mg per liter. Next question, again theoretical, very easy. Again, sequence rate, sequence of matching. This one is the matching. List one and list two. Okay, I got answer from Ruchita, Nilke, Nikhilesh. That is B, right? So we'll check here. B, that is a grid chamber, is associated with Stokes law. Fine. Then the secondary settling tank is set zone settling. Good. Then activated sludge process is aerobic process, and then this trickling filter is contact stabilization. Fine. So the next question, again numerical, same thing, same type of question. Overflow rate is given, depth is given, and you need to calculate the diameter. Flow rate is given. Just quickly answer. Who were there couldn't solve earlier, now you should able to solve this, because I repeated this kind of question many times in today's session. So now at the present moment, all should answer this. Yeah, very good, Ruchita, 8.5. Okay, then Nikhilesh, 8.5, fine.
This is 8.5.
Okay, good, very good, Abdul, 8.5. So same thing, Q is 900 meter cube per day and surface overflow rate is 16 meter per day. So surface area will be Q divided by this flow rate divided by surface overflow rate, and there is nothing but 56.25 meters square. Then pi d square by 4, this area equals to, if you want to calculate for d, you can get as 8.46 or whatever you are getting. It depends upon the calculation. Right? So find 8.46 or 8.5. That's good. The next one, you have to match one function or principle to the types of treatment.
This answer is C.
Abdul, very good. You are saying answer is C, and then I got two more answer from Ruchita. You were saying A and Nikhil's A. Right. So the correct answer is A, and we will check why it is the correct answer. So the first one is the correct answer. It is as a pre-treatment, and pre-treatment is nothing but the grit removal. I already discussed this in the previous question. Some previous question it was there, the pre-treatment as grit removal. Then the suspended growth biological treatment, and this is the aerated legume. Then the attached growth biological treatment, nothing but trickling filter. The last question was related to this, that maybe last or the some previous question. And then this disinfection is for the UV. Again, matching according to CPHEO. There is a manual for all the parameters which are discharged into the surface water. So you have to check the parameters and what is the higher limit that you can discharge into the surface water safely. That's what you have to think for this question. This is a information based question, so try your best to answer. Okay, I got answer from Nicholas C. First answer, very good. Okay, Ruchita C. Fine. So no need to wait. So we'll go for the solution. The correct answer is C. Fine, very good. So you go to this manual, right? So if you just go for to this manual, Central Public Health and Environmental Engineering Organization, it is a wing of Ministry of Housing and Urban Development. If I'm not Urban Affairs, I guess, yeah, I'm Urban Affairs. So go to their website and try to download. It's easily available on internet, and please check what is the limit for surface water discharge. So no need to repeat. This is the correct answer. See, please go and check the manual. You will get the information. Next one, pre-treatment. Okay, I can skip the same question repeated. This one also repeated question, right? Fine. Now question number 16. For a grid chamber, if the recommended flow velocity is 0.32 meter per second and the detention period is 1 minute, sorry, then the length in meter of the tank is, that's what you have to calculate. What is the length of the tank?
It is 19.2 meter.
Very good, Abdul. 18.2 meter. You are saying that Ruchita is saying
Nin-
19.2.
19.2.
Okay, okay, fine, fine. Good, 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 very good. Yeah, I'm getting very positive response. So 19.2, right? Yes, 19.2. So flow velocity is 0.32 meter per second, and detention time was 1 minute, that is 60 seconds. And length is very easy, right? You need to just multiply with flow velocity, like you need to multiply flow velocity with detention time, and you will get your desired answer as 19.2 meter. So this one is theoretical, again regarding the sedimentation tank, the efficiency of sedimentation tank. Ruchita, good. C,
That,
fast.
i- that is C, increase in the surface area of tank.
Yeah, yeah, very good, Abdul, very good, Nicholas. Okay, so the correct answer is C, increasing the surface area of the tank. Not related to depth, right? So very good. And this one is regarding the aerated grit removal. Which statements are correct?
That is, answer is a tank that is typically positioned parallel to the axis of the spiral rod.
Okay, good. So you are saying A, right? What about others that we can? Okay. Nikhil's is saying A. Right. So, is there any other statements? Because multiple correct statements are there, not only a single one. We'll go for the solution. So the B and C is the correct one. That aerated grid chambers are versatile, which allow the chemical addition. You can add the chemical, or maybe in the purpose of coagulation, or it has a consistent removal efficiency over the wide flow range. So that is the two correct statements. These are not true. Again, conceptual question regarding the grid chamber. The design goal of grid chamber is to provide sufficient detention time for the grid to settle while maintaining constant velocity to scour organics. Is it correct or not? Okay, Nicholas, Ruchita A, right, Nicholas A, fine. Yes, that is true. Yes, Nicholas A, right, right. So that is true. The design goal of the grid chamber is to provide a sufficient detention time to settle the grid, as well as you should scout the organics. If organics are going to settle inside the grid chamber, it will be a different chamber, not a grid chamber, right? So in case of your grid chamber, there should not be any organics settling. So it should scour from the bottom. You need to degrade these organics inside your secondary treatment tank or your activated sludge process, right? Otherwise, your grid chamber will become activated sludge process. So next one regarding statements, not the single statement, but statements regarding type 2 settlement. Can Nichilas A and C? Anyone else want to answer? Ruchita A and so the correct answer is A and C. Particles collide with each other and agglomerate, leading to the population settling, and then due to the velocity gradients within a liquid cause particles with higher velocity to overtake those in the adjacent stream paths moving at a slower speed. So these two incidents will happen due to the velocity gradients within a liquid. So it will cause the particles with higher velocity to overtake those in the adjacent stream paths moving in a slower speed. The next question, find the terminal velocity of spherical particle diameter of 0.5 millimeter and specific gravity of 2.65 settling through water. You have to find out the settling velocity. You can refer to your book for the formula. You can refer to your notes for the formula if you need. Try to calculate this very quickly. This is question number 21, I guess. You may need to do some trial and error for this question. For this particular question, you may have to go the method of trial and error. So be careful and then answer. Okay, I got an answer from Nikhilesh. The first answer, very good. 9.22 centimeter per second. I will wait for 2 more minutes and then go for the solution. Okay, we'll go for the solution. Right. So the correct answer is 9.22 centimeter per second. So congratulations, you guys very good. You solve very quickly. So what is here? First, we have to assume it as laminar flow, right? So in case of laminar flow, from here we will start and we'll do trial and error, try to get the right answer. So in case of laminar flow, we know what is the Stokes formula. So this is my Stokes formula in case of laminar flow. It's normalized for in case in the situation for laminar flow. I'm getting rho g, then g capital G minus 1 and t square by 18 m. So rho is nothing but for water 1000 kg per meter cube, the density, and then the G is 9.81. We'll put this capital G value as 2.65. This was the specific gravity of the spherical particle, right? So it is 2.65 and minus 1 multiplied by diameter. Diameter is given as 0.5 mm. So you can write it as 5 multiplied by 10 to the power minus 4. So I'm converting from millimeter to meter and then square. It's as simple as that. Then 18 multiplied by 10 to the power minus 3, because how I'm getting mu as 10 to the power minus 3, refer to the first question. We already calculated mu as 10 to the power minus 3. So go back to that question and you will get how I'm getting this 10 to the power minus 3 in case of water. So Vs, the settling velocity here is 0.22 meter per second, right? And then you have to check the Reynolds number because our assumption was that it was laminar flow, but it may not be laminar flow, right? So you have to check the Reynolds number here. So Reynolds number is nothing but rho d Vs by mu, right? So the rho in case of water, the density is 1000, and d already diameter I calculated as 5 into 10 to the power minus 4, and then your settling vessel velocity, how much it was, 0.225 meter per second. Just put the value of mu, calculate. It is I'm getting as 112, like 100 and 112.5. So this is greater than 100, so we can indicate it as transitional flow, not laminar flow. So our assumption was not true, right? It was not true. So now we have to calculate for transitional flow. Then there will be the drag coefficient CD. It is my drag coefficient for transitional flow. That is nothing but 24 divided by RE Reynolds number plus 3 divided by RE to the power 0.5 plus 0.34. So if you put this Reynolds number 112.5 to this equation, you will get CD or the drag coefficient as 0.3, sorry, 836, right? Then again, you have to calculate what is the Vs settling velocity for transitional flow, and this is the formula for your transitional flow. That is 4 by 3 GT capital G minus 1 divided by CD, that coefficient. So you calculated what is your CD value, 0.836. Put it here, the down, and you know what is the G value, T value, and this G is nothing but 2.65, right? Calculate the Vs, you will get 0.1133 meter per second, and then use this Vs or the settling velocity and repeat the steps, step number 2 and 3 and 4 even. So what you will do, you got this Vs, right? Then check the Reynolds number. Put this Vs or the settling velocity 0.1133 to this equation, Reynolds number. Check how much Reynolds numbers you are getting. So I'm getting Reynolds number as 56.65, right? Then what you have to do, then put this value to the equation number 3 here, CD. Calculate this CD. CD I'm getting as 1.16. Then again calculate your VS, the settling velocity. It is 0.0965 meter per second. Then check these two, tally these two. Are they equal or not? No, they are not equal. They are not matching, right? This is 0.1134 and this is 0.0965. So these are not equal. So you need to go like this, trial and error, to match both these VS values. If these both settling velocities values are matching, you can say that's your answer. So again, try with this new settling velocity 0.0965. Go repeat this step 2, 3, and 4. I'm getting again Reynolds number as 48.25. Then your CD 1.27. At the end, the settling velocity I'm getting at 0.0922. So now you can check this was 0.096 and this is 0.0922. So these are closely equal. So I can end that my desired result is 0.096, or you can also write as 0.0922 meter per second or 9.22 centimeter per second. I hope this one is clear for everyone. Please confirm this is clear. You can check.
Hello, sir. I want I have some confusion. What is
Uh,
the mu? Reynolds number is equal to rho d Vs divided by mu. What is mu?
yes.
That is 10 to the minus 10 to the power
Okay.
minus
Yeah. Yes. Yes. Right. 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 So that's why I told you to refer the first question. This is dynamic viscosity here. So just give me some time. So mu is the dynamic viscosity, and for water it is 10 to the power minus 3. And you just go to the first question. Actually, it was calculated there. So just check this question. Here it was given as the kinematic viscosity of the liquid. Basically, it was water. That's why you can check the density as 1000 kg per meter cube. So kinematic viscosity was given as 10 to the power minus 6 meters square per second. In Reynolds number, in case of Stokes law, we use the dynamic viscosity, not kinematic viscosity, and this is mu. This is kinetic viscosity multiplied by the rho of the density of your liquid or water, whatever is your liquid. In the last question, it was water. Here also, it is water only. So the kinetic viscosity was 10 to the power minus 6 meters square per second multiplied by 10 to the power 3 kg per meter cube. This is the density of water, and I'm getting 10 to the power minus 3 kg per meter second. So this is the unit for dynamic viscosity.
Hello, sir. Here is 10 to the power minus 3 kg. Uh,
Yes,
yes. Kg per meter per second is a kinematic viscosity.
yeah, this is the
That is
dynamic.
K. Value of K.
Mhm. Okay, let me check. K was in meters square per second, right?
Kinematic viscosity. What is
Yes,
K?
that is the kinematic viscosity.
Okay, multiplied by density.
Yes, yes,
Density.
right, 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 right,
We get dynamic viscosity. That is mu 10 to the power minus 3 kg per meter per second.
right, right, right. Absolutely.
Okay, okay, okay. Thank
Now clear, right?
Yes. One thing more,
Uh-huh.
this dynamic viscosity, whatever is given is it in certain temperature or it can be vary with temperature?
Yeah, viscosity can vary, but if there is nothing mentioned, no mention of temperature, you can just go as it is. Right? Even the density also changes. Intensity of water changes with the temperature. At the 4 degree temperature only, we are getting this whatever we are calculating with respect to 4 degree temperature. So in case of water also the density changes, also the viscosity will change. But better if there is no mention of any temperature, you can just go with that. But in case of most of the questions you will face, or the real life situation, there will be not much variation. So you can just go with some fixed value.
Okay, thank you, sir. One. I have one more question. Whatever value is given here, I want to know just in next session in which temperature this value is given, and I have to consider for calculation. But just I want to know the temperature in next session, sir.
Okay, okay, sure, sure.
Thank you.
So thank you. This was the end. Hope all of you enjoyed today's session, and we will meet on the next session, the next week on Tuesday. Thank you, everyone. Thank you again for your participation.
Okay, thank you, sir.
Thank you, Abdul. Thank you, Ruchita. Thank you, Nikhilesh. Yeah, thank you. So you may leave now.